Like usually that's like if there's a physics exam or something, you guys are distracted. Yeah, well, let's see, sacrifice my chemistry grade for an extra 2 points on the physics exam. Anyway, so we are, I just started the next chapter in Gen Chem. There it is, the hat makes an appearance. Do you want to get on camera with it?
Right.
Come on, now's your chance. Look, 7 people will watch this, okay? All right. Anyway, so we had just gotten into the new chapter where we're dealing with the overall topic of Gibbs free energy, and just if we want to think of an overarching theme, we're kind of just looking to answer the question of, why do reactions happen and how do they happen, and we'll talk about terms like spontaneity and entropy and enthalpy, like just looking at how energy transfers through a system is what it is. And so the first part of the chapter we dealt a lot with entropy, and we just kind of established some of the ground rules for that. With respect to just what does it mean, right? We all have these definitions of entropy that we've heard colloquially, disorder and all this kind of stuff, and that's fine, right? But if you want to really impress your friends, now you can talk about accessible energy states, and they're just going to be fascinated by that, I'm sure, right? But that's kind of what it means in the chemistry sense here, right? You can spread energy out over a larger number of things, right? And so we did a couple of visualizations there, right? The bromine, I think it was bromine gas, whatever, expanding over different 2 different volumes there, these kind of things, right? And so then we came into kind of, let's say, the first really important conceptual idea that comes out of this chapter, and that's this idea for the qualitative guidelines from entropy there. How can we predict the entropy change or the entropy of a system? And we walked through a couple of different things to pay attention to there, just to see if we can answer the question of will entropy decrease or increase for a system, okay? And so we talked about how gases have a higher entropy than liquids and solids. Right, we talked about playing the accordions, we talked about bending and stretching and moving and all that kind of stuff, right? So that's what we mean by forward motion, right? We're not just translational motion, right? But rotations and bending and flexing and all that other kind of stuff also. Right, we talked about the bigger the molecule, the more entropy there is, and that has some impact on some of these factors that we'll talk about in biochemistry and organic chemistry also. We'll talk about how these different accessible energy states exist. We talked about solids and made arguments about Coulombic attraction, right? The higher the charge of an ion, that it's going to be attracted more to its opposite charge, right? A +2 is going to attract a -2 better than a +1 is going to attract a -1, right? There's going to be a better, let's say, set of communication between those two is what it is, okay? So that's something that we can use to predict entropy. We talked about dissolving something, right? If we can put stuff in the solution. We talked about why it's different for gases or things to pay attention to there. We talked about making more stuff or converting solids to liquids or gases to gases and some of these other things here that came across with these qualitative assessment. And then I think this is where we had ended up last time, right? We said, okay, now that we can qualitatively look at these things and assess the magnitude of S, right? So all the previous slides there, just to get to the point of, hey, is entropy going to be a positive value or a negative value, okay? Because what we're going to get to today is we're going to string together a formula based off of enthalpy and entropy, right? And one of the important questions that come out of that is this going to be a spontaneous reaction or not? So it's not going to be necessarily important that we know the exact value of entropy. It's that we know its relative magnitude, aka is it going to be plus or minus? Is it a big plus or a big minus? That's going to be the assessment that we make with this. So everyone following along with that, right? We're going to put some numbers with this stuff, but it's not just what the numbers are, it's also, is it positive or negative, right? A positive value means we're increasing entropy, a negative value means we're decreasing entropy, right? Good? All right. So I think that's that, in terms of the recap that we had there. I will, downgrading the exam, so I will have everything back to you guys on Friday, and then I'll make my comments about it then. Just one kind of thing for me to take care of before, otherwise I'd have it back for you guys today, but I promise on Friday we'll have all that stuff back for you guys, okay? We'll open up a quiz for you guys for Monday, based off of the stuff that we've been going over there, okay? So just keep an eye out on that. And I think that's kind of all of the pre-class stuff I need to talk to you guys about. Yeah. Okay, cool. Then let's get started with prayer, and we will then continue on through the slides here. But Lord, we just thank you yet again that we can turn to you in prayer whenever we want, Lord. And Lord, we just pray that the time that we spend talking with you and the time that we spend with you, Lord, just settle that on our hearts, Lord. Just help us to understand, and help us to know, and just help us to feel your presence more this day, Lord. We know that the time that we spend with you is always for our betterment, Lord. And so just to help us to, ignite that spark with us, Lord, just to want to spend that time with you, Lord. Just to give us that faith and help that faith to grow. And just help us to be able to express that faith to you, Lord, just with the conversations that we have with you and the time that we spend just meditating on the things that you've done in our lives, Lord. We just pray for the blessing of this day. It's another beautiful day filled with sunshine and just an opportunity for us just to live and be good and faithful servants to you, Lord. So we just pray that we have those opportunities, and we pray that you put the people in our way that we can share you with in whatever way that might be. And we just pray this in your name. Amen. All right. So here is one way that we have of calculating entropy. It's nothing fancy, right? A change in entropy, right? Remember that capital delta there, the triangle just means a change in something, and a change is always final minus initial, right? Products minus reactants, where you end up minus what you start, right? That's all it is. And so if you take a look for the entropy values, which you can just look up, and there's, I forget exactly what table, I didn't look at it again, I apologize, but I think it's like Appendix C or E, I forget. But in the back of the book, I think they've got lists of these molar entropy values, right? And so if you have a balanced equation, right? Make sure you have a balanced equation with the states that are with that. You can just look up, right, the molar entropy values for those things, right? So if we look for methanol as a liquid, right, it's got a value in there, and carbon dioxide as a gas, and oxygen as a gas, and water as a liquid, right? We can just pull those values in there, okay? And let's see, did I ask you guys to work this through, or did I give you guys a blank space here? Okay, so a little bit of blank space here for you guys to kind of work this through. But I think you guys kind of get the point here. So our delta S naught is equal to the sum, right, of our products minus the sum of our reactants. So in this case, right, we would have 2 times S naught for CO2, okay, plus 4 times the S naught for water. Okay, so there's our products minus, let's see, 2 times S naught for methanol, we'll just abbreviate that as NaOH, plus 3 times O2 as a gas. Oops, that's not what I want to do, S naught. Good. And you just fill in the values that we had there in the previous slide, plug it in, you're gonna get a value for S naught. Pretty easy, right? Nothing too ambiguous about this. Just filling in the blank. And 161.90 joules per mole Kelvin there, right? There it is. Okay. just a little bit of a quick summary here, right? We talked about this a bit, but just to bring back the idea. So the dispersal of energy, aka entropy, right, is accompanied by the increasing disorder of a system, right? So increased disorder means increased entropy. That's what we've been talking about all along. Got it. Okay, there's the second law of thermodynamics. The total entropy of the universe is continuously increasing, right? So everything tends towards disorder, and we talked about your room, and when you have to clean it and all this kind of stuff here, right? So this is kind of just bringing back those two ideas that we had mentioned earlier. To say that, right, the entropy of a system can increase or decrease, right? So an individual system, right? So if you're doing a reaction, we can increase or decrease entropy with that. But the entropy of the universe always has to increase, always has to go up, right? Now the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings, okay? Now that should look familiar because this is similar to what we did when we're dealing with enthalpy, right? We talked about there that the enthalpy of the universe has to remain constant, so something that was gained, right, had to be an equal amount of that had to be lost somewhere. And we talked about systems and surroundings in terms of how heat energy is transferred between systems, right? So exact same idea here. For what it's worth, when you're working through some problems and things, if you just see an S, we assume that's the entropy of the system itself, okay? So we should just paying attention to exactly what is the entropy value referring to. The third bullet point there basically says that if the two bullet points above it are true, that means that if S of the system decreases, right, the S of the surroundings must increase by a larger amount, okay? Entropy for the universe must always go up, so if this decreases, right, if this decreases, then that has to be the opposite magnitude, but a bigger value, okay? And so if we want to bring in the equation that we had talked about on Monday there, right, that the entropy of the surroundings is equal to the Q over T, right, which is equal to our enthalpy, right, but our enthalpy of our surroundings is equal to enthalpy of the system here, right, the negative of that, okay? So we did a little bit of I think we did one practice problem there, just recalling what enthalpy is and just paying attention to when Q is equal to delta H and those kind of things associated with it, okay? So the change in entropy of a system is equal to delta H over temperature, right? Yep.
How can something be conserved if it's continually increasing?
How can what?
How can, for example, like the entropy of the universe be continually increasing yet conserved at the same time?
It's not conserved. Or what do you mean by conserved?
Well, the universe, the entropy of the universe is the system plus the, what's the second one mean?
Surroundings.
Surroundings.
Yeah.
Then how can it continually increase if, say, the system decreased, then the surroundings had to increase?
Correct, yeah.
Okay. So how could the system or the universe continually increase if those reactants, if you will, are always accounting for it?
You're asking me to derive the second law of thermodynamics real quick, and then just. I mean, that is essentially what you're asking, which is, I'm not saying it's a bad question.
Yeah.
Right. I mean, but there's a tremendous amount of explanation that goes into that too.
Okay.
It's maybe not to oversimplify your question, but you're saying like, how in the world is that possible? Right? How do we just continually produce something?
Yeah.
Right? It's very different from what we're used to, right? We're used to conserving something, right?
Right.
One egg makes one omelet, right? What we're saying here is one egg can make 3 omelets, right? To put a simple explanation to it, right?
Okay.
So it's a great question, right? And it doesn't have a short answer.
Okay.
So what I will say is it's just one of the laws of the universe at the moment, right?
So I'm glad I asked.
Yep. All right. So see what you guys come up with here, right? Using the equations that we have there on the previous slide. So calculate the entropy of the universe, or the change in entropy of the universe for the combustion, and then it gives you guys some values of stuff there, right? Delta H's and delta S's, all these kind of things. change in entropy of the universe. And so S of the universe is equal to S of this system, right? Plus S of the surroundings. We're given a value of delta S there without a subscript, right? So what did we say about that?
S of the system.
It's our S of our system, so we need to figure out S of our surroundings. And what's that equal to? Right, that's delta H, right? Over T. Don't forget the negative sign, all right? Don't forget the negative sign. Negative delta H over T. Good. Something important to pay attention to here, though. Something important to pay attention to in every single problem that you work in Gen Chem. Delta H is in units of kilojoules, and delta S is in units of joules per Kelvin, right? So make sure you convert either joules to kilojoules or kilojoules to joules, okay? So if we put all this together, we have negative 1, so it's supposed to be red. Let's change that up real quick. So our system is negative, all right, I'll try this for the third time. Negative 138.3.9 joules per Kelvin. Right. Plus, there it is, right? Plus our negative, right? Our negative of our negative 11.024 kilojoules, right? Let me just make myself some space. And we can go ahead and multiply that by 1,000 here, right? Set up a really scary looking equation. Apparently I cannot write this morning, so not enough coffee, makes sense. Okay. So S of our system, right? Surroundings is delta H over, or negative delta H over T. There's our delta H. We convert it into joules over our temperature, add this stuff together. Good? So what's the tricky part? What's going to be one of the tricky parts coming out of this chapter? Just keeping track of what all the different values represent, okay? Which one's the system, which one's the surroundings, where's my negatives, what are my units, all this kind of stuff with that, okay? Yep.
So the delta H isn't just for the surroundings, it's like, or for the system, it's for each part of the. Does that make sense? You said, cause like delta S is like for the system,
Yeah,
right? And delta H
for the surroundings.
for the surroundings.
Yeah.
Okay, and that's
Now
just one.
now the entropy of the system and the surroundings are related too, right?
Okay,
Yeah.
okay.
Why are there two negatives?
So delta H is negative 11, right? And then the value for, here, let me just scroll up here because I have to erase it. Right? The negative of our system is equal to our surroundings there, right? So if one's positive, the other one has to be negative.
So for delta H, would you assume if there's like no subscript that For surroundings?
Yeah,
Okay.
so usually I'll try and be very clear with you guys on this, but when we're talking about in the book, right, that's the assumption that we can make with that. Okay, so now, okay, we get to this point here, and then we can finally get to one of the big equations that come out of this chapter, right? So neither entropy nor enthalpy alone, right, can predict whether a reaction is favored. It's got to be a combination of those two, essentially, is what it is, right? A spontaneous product favored reaction can be exothermic or endothermic, right? We talked about that, so that, you know, that means that enthalpy by itself can't predict what happens, right? And, right, the spontaneous reaction can increase or decrease the entropy of the system, okay? So that's all we're saying with that, right? If we take that statement at top, essentially those two bullet points are the conceptual idea coming out of those, okay? So what we have to do instead is look at something called Gibbs free energy, which is our way that we're going to have of predicting the spontaneity of a reaction, okay? So if I ask you guys on an exam or a quiz, say, hey, is this reaction going to be spontaneous? You got to go look at your Gibbs free energy, okay? That's one way of doing it. And Gibbs free energy is represented by G. That's great. If you take a look, it's going to be based off of enthalpy and entropy values there. Okay? So all this comes together to, right? So you guys don't have to copy this down necessarily, right? I think on the next slide that you guys have, we have that up there, but I just wanted to show you where this all comes from. So if we start up there with the equation that we were just using, right, we substitute entropy for the surroundings, we multiply by the negative temperature, we can rearrange, right, and then we get to, we define Gibbs free energy here as this, right, and we essentially get to the equation that we're going to use there is what it is. Right, so that delta G is equal to delta H minus T delta S, okay? That is probably the slide that you guys have, right? For a constant temperature change, delta G is equal to, okay? So what does this mean for us, right? If G decreases, aka the delta G is less than 0, okay? A negative value, the reaction is product favored, okay? If it increases, the reaction is reactant favored. Now we have to hold this at a constant pressure. Okay. Good? So product favored versus reactant favored. Yeah, what's up?
What is a constant change in temperature?
What do you mean?
Like, what is a constant change in temperature? Because the bottom says constant temperature.
Yeah, for G itself, right? G versus delta G, right? Yeah, that's all this. Yes. Cool. All right. So as a big shock then, okay. Oh, sorry, I got a little bit ahead of myself. Next one's going to be the big shock. So if delta G is negative, the forward reaction is spontaneous. That's all we're talking about here, okay? I believe this is just a page right out of your book, right, where we just graph free energy versus one of these reactions here, okay? If delta G is equal to 0, then the system is at equilibrium. Aha, so now we are going to start to see this little bit of an idea of equilibrium come back into play is what it is. And so we're going to see in a couple slides, we're going to bring an equilibrium constant into an expression of delta of G, okay? If delta G is positive, the reaction is not spontaneous, but spontaneous in the reverse direction, okay? So these are just another way of saying what the two bullet points are there on the bottom. Right, and there's a graphical representation of that over there. Okay? That's all we're saying. Taking a look at whether delta G is positive or negative, and what does that tell you? It tells you about the directionality, right? Is it forward or reverse? And is it spontaneous in that direction? Right? kind of like, well, not kind of like, exactly like the idea that we had with equilibrium, right? We have to define what we mean in forward and reverse rule, okay? And so, when you're looking at a reaction left to right versus right to left, right, if you switch it over, right, we're going to change what delta G is for that direction, right? Does that make sense? Right, we're kind of just doing the same thing we did for equilibrium, but just putting a different letter with there now. Okay. So delta G can be calculated from delta H and delta S values. That's what that, the equation says. Or if you take a look in the book, they've also got Gibbs free energy of formation values, delta GF, or delta G sub F, I should say. Now, I'm not going to belabor this too long because I think you guys understand this at this point, right? Products minus reactants. And if we have those G values, then we can just calculate what the Gibbs free, or what the delta G is for this reaction.
And N just refers to the balance coefficients?
Yeah, the stoichiometry. Because, right, the delta G values are per mole of compound, right? Good. So you guys starting to get a little bit of a pattern here for what's going on, right? If you take a look in the back of the book, there's tables of delta G values. And right next to those, there's, I shouldn't say delta G, there's tables of G values, and H values, and S values. Okay, and all of those are linked together, okay, using the equation that we were just introduced there. So you can figure out delta G and delta S and delta H, right, depending on the information that's given. Okay. Something important, okay, we noticed this wasn't the case for entropy, okay. 0 for an element in its most stable state, right, aka its elemental form, might be another way of thinking that, right, is going to be 0, okay? 0 for an element in its most stable state. We did see that when we talked about enthalpy, okay? We did see that when we talked about enthalpy, but not for entropy. So this is one point of confusion, okay? Remember, the formation of something, the enthalpy of formation for something in its elemental form is 0. Okay? Its entropy is not. Okay? Entropy is not going to be 0 for something that's elemental form. But it is for delta G and it is for delta H. Okay? I believe you guys got a problem or an example next here. Yeah. So, typical question, calculate delta G for the following. Give an equation. You look up the G values. Yada, 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 put everything together, okay? We see that hydrogen, H2, in its gaseous form, that's its elemental form of hydrogen, okay? So its G value there, the delta G value is going to be 0 for that, okay? We add it all up, negative delta G means it's a product-favored reaction, okay? That means if we mix carbon monoxide plus hydrogen gas, it's going to make methanol. Okay. Pretty important reaction. If we get a chance to talk about environmental chemistry towards the end of the semester, we'll probably come back and take a look at that reaction again. Right? It's pretty important for the state of energy for the world, right? But different conversation. Good? That's not too bad. Okay, so then the question should become, right, reactions go from reactant to product favored when delta G is equal to 0, which is equal to delta H minus T delta S. AKA, when can we shift from a product favored to a reactant favored? At what temperature does that happen? Okay. So essentially to answer that, right, T is equal to delta H over delta S. That's going to tell us the temperature where product versus, right, the G value goes from positive to negative at that point, okay? And this is just kind of the idea behind that here, right? So that's probably the important part of the slide there, the little bubbles there, if you guys can see that. Or in the back, it might be an eye exam, I hope, right?
So that's the temperature when it's at
That's like before or after that is where you switch from the positive to negative for delta G, right?
How did those units come out?
Well, S is it for here. So remember, this is per Kelvin, right? And so, 1 over Kelvin is going to end up in temperature units, is what it is. And the rest of it's all energy, right? So they're gonna cancel out. Good. All right. So one more idea, and I think we've got a practice problem coming up here. But this is probably one of the most important slides. Okay. Typical questions to come out of this chapter are, like I said, predict the spontaneity of this reaction, right? Is it going to be product favored, reactant favored? And our delta G equation there is going to be what's useful for this, okay? So to be able to predict this, right, we're going to have to know the sign of delta H and the sign of delta S. Are they positive values? Are they negative values? Okay? So I have 4 different scenarios here for you. If delta H is negative, right, remember that means it's exothermic, right? That's all, I'm just giving you guys a reminder there. So if we have an exothermic reaction and the sign of delta S is positive, okay, then it's going to be a product favored reaction. So let's think about this, right? So here's what we're saying there for scenario 1. Where's my blue color? There. Okay. All right, so delta G, right, is equal to a negative value, right? A negative value for delta H, right? Minus, right? A positive value for delta S. You guys with me on this? So what happens when you multiply a negative times a positive? You get a negative value. So if delta H is negative, and the T delta S is going to be negative because S is positive, then delta G has to be negative. You guys follow along with this? This is important, okay? You guys can memorize those 4 if you want to, that's fine, right? I'm just trying to explain to you how, if you don't have to memorize those, if you just think about what the equation tells you, okay? If we go down here to the bottom end, right, if delta H is positive, and delta S is negative, this is plus, a negative times a negative is going to be a plus. That means that delta G has to be a positive value. So it's not going to be spontaneous in that direction. You guys with me on this?
Why are you multiplying delta H and delta S?
Well, T delta S, I'm sorry, ask your question again?
So why are you multiplying delta H and delta S?
Well, I'm not, I'm just following the equation there, right? We put the negative into the T delta S part, right? Remember, a negative is the same as plus the negative of that, right?
Okay.
If you want to think about it that way.
And what is G if, according to the sign, what is the sign that makes it product favored of delta G?
What are we looking for? Yeah, so a negative value is going to be spontaneous in that direction, right?
And what does that spontaneity mean? Like, is something spontaneous if it produces if it's product favored?
It depends on the direction that you're looking at, right?
Yeah.
It means that reaction will happen. It doesn't say how fast, right? It doesn't say how fast, but it will happen eventually.
That's what spontaneous means?
Correct. Correct. I'll give you guys a good example. I think the last slide maybe has the best kind of visualization or idea of that, but we'll talk about that. Okay, so at the top of the bottom, you've got your 2 extremes, okay? You've got a negative and an overall negative, right? And so that means delta G has to be negative, a positive and an overall positive, so delta G has to be positive. And the 2 in between is where we have to pay attention to temperature, okay? So if you've got an exothermic reaction here, right, a negative delta H and a negative delta S. So remember, when we have a negative delta S, right, you have to think about what that means over here, right? Let's think here for just a second. change colors. Red. Okay. So delta G. Right? We've got a negative value for our delta H. Okay? And if delta S is negative, right? So minus, okay, a minus times a minus. So here's the part where we have to pay attention to temperature. If you've got a big temperature, right? If you've got a high temperature, what does that mean about our negative over there? That's going to dominate our equation, okay? So it looks like this. So we've got a little negative there for our delta H, right? And a big negative for our delta S. Got it? The T there, the temperature, is the part to pay attention to, okay? The bigger the temperature, the more the entropy dominates the equation. And the more the sign of our entropy dominates the equation. Right? Because it's T times delta S. Got it? So that's what we're talking about here. At a low temperature, our delta H is going to predict, right? At a high temperature, our entropy is going to predict what happens with our delta G. Good? And then the opposite is true if we switch things around, right? If we've got positive and positive, then we have at low temperature versus at high temperature, we switch those things around. Think about this slide for a little bit. See if you guys can come up with the same answers that I did for this, okay? This is one of the important things to process out of this chapter, okay? Because we have values for delta H and delta S, right? How does that affect our delta G based on our equation that's up there? What is the value of delta G? Is it a negative or a positive? And what does that mean about spontaneity? Okay? All right. So I've worked all this stuff out here for you guys, just because otherwise it'd be an exercise in looking up stuff in the textbook. But it'd be useful if you guys could do this on your own too. So quick question, at what temperature will the following reaction be product favored? Okay, AKA, where will it switch, where will delta G switch from positive to negative? Okay. So we can get our delta S value, right? Our products minus our reactants. We have our delta H values, products minus reactants. Don't forget for delta H, right? The delta H of formation for something in its elemental form, right? Which is H2, right? Is equal to 0. Right? We have our two values, delta H over delta S is equal to this. Right? So here's our temperature where delta G will change signs. Okay? Where it'll go from product favorite to reactant favorite. Lots of numbers, huh? Okay. So just as a kind of a little bit of this and that, we got a couple of slides here. So if we've got sodium hydroxide and carbon dioxide, we can make sodium bicarbonate, delta G of negative 77, right, 0.2, right? And we just have an extent of the reaction versus the G, right? So how can we measure G? How can we back out G, these kind of values here? Right, so graphically we can take a look at this stuff too. It's kind of just all we're saying here, right? So Gibbs free energy decreases continually as a reaction occurs, okay? Which kind of makes sense if you're thinking about it, right? Because we have to remember for this reaction to happen, we have to have these two things come together. Okay? They're going to form some kind of equilibrium, but we're eventually going to be consuming one side versus the other. Okay? So G gradually decreases is what the important thought that comes out of this slide is. So if a reaction reaches equilibrium, right, G instead reaches a minimum, okay? And so this is similar to the other graph that I had previously for you guys here, right? So depending on where we are, there will be a, let's say, a trough, a bottom point, a valley to our graph here. And that's where G reaches a minimum. I'm not saying it equals 0, right? That's not what I'm saying. I'm just saying where it reaches the minimum value, okay? Maybe you can see where we're gonna bring in the value of our equilibrium constant here. All right. So the Gibbs free energy and the equilibrium constant both show if a reaction is product favored and how they're related to each other. So there's our next important equation to think about. So delta G is equal to RT, natural log K. So we're dealing with R values, so pay attention to your units of temperature, right? We're dealing with R, right, then our temperature better be in Kelvin also. So just looking at the units for the different components in this. All right, so I've talked way too much. So let's see what we can come up with here. So basically figure out K for this following reaction. So what we're going to need is a couple of bits of information. Okay? We're going to need our delta G naught, right, of formation, our delta G naught F. Okay? And don't forget that that equals, right, the balanced equation there, right? The products minus our reactants. The delta, the G values for those. So if we take a look in our book, let's see, we got GF for N2O4 is equal to 97.89. GF naught for NO2 equal to 51.31. Or did I switch those up? No, I got that. Okay. So where did I get those values? When you have a problem like this, look for the tables in the book. Okay? They're not always going to list the delta G values there for you guys for some of the example problems. So either a table in the chapter or a table at the end of the book. Okay? You can pull those values from there. Then what we have is our products, right? So 97, page 9, minus 2, times 51.31, is equal to negative 4.73. Products minus our reactants. Delta G, right, equal to negative RT ln K, right? So now we've got a value for delta G, okay? We've got a value for T, and we know that R is equal to a constant, right? So now we just need to back out K naught from that equation there. So see what you guys get to. So rearrange, shuffle, use the numbers that we have, back out a value for K. Yeah, basically.
Excuse me, what's R again? We're at 0.08 or
Aha, good question, right? So, there's a couple different values for R. Okay? The one that's 0.08206 is in liters, atmospheres, mole, Kelvin. Do we have anything to do here with liters? Nope. Okay? So we're gonna need our one that deals with energy, right, which is the 8.314, right? Joules per mole Kelvin, is what it is? Yeah, joules per mole Kelvin. Mm-hmm. 8.31. So how do we get rid of our natural log there to isolate K naught?
E to the
E to everything else, right? So getting rid of a natural log is E. Getting rid of log base 10 is just raise everything to 10, right?
no, that's log. Like in log. It's interesting.
So at the end, I got everything. I got K naught equal to about 6.75, right? So what does this tell us then? Well, that's just a value of K, right? I think we just spent the last 3 chapters studying K and looking at it. So hopefully this K here isn't any different than what we're familiar with. Cool. We just have one more slide for you guys, and that'll actually be it in terms of the lecture. So we'll spend the rest of our time kind of looking at some practice problems. Okay?
How do you get that for the
Yeah.
last one?
Did I get something wrong? Maybe I put something wrong. What's up? What did you guys get?
I got 1.
Oh yeah, 1.0.
You guys got what? 1?
Yeah.
So, let's see here, we got negative 4.73, right? Over 8.314 times 298. And that was equal to, E to that is equal to 1 is what you guys got. Let me go double check what's happening then. I did get that. But maybe I typed something wrong in my calculator here too, so. I don't know. You guys removed your negative sign and everything, yeah? Okay, let me double check that, and I'll come back with you guys and see, where the issue's coming in. Okay. We'll see what's going on. Okay, so one last thought here. Okay, thermodynamically stable versus kinetically stable. It's unfortunate that this is kind of, again, one of these one of the most important things to come out of this chapter. It like kind of comes at the end, and we're all kind of, I guess, number drunk at this point, where we have all these different equations and numbers and deltas and g's and all this kind of stuff. But this is going to be extremely important when we talk about how we actually isolate certain reactions, especially in organic chemistry and especially in biochemistry also. Okay? Thermodynamically stable, right? So what we mean is the reaction is not product favored, right? Okay. And kinetically stable, product favored, but too slow to be important. Okay. So whenever you see these terms kind of thrown around, we're referring back to this idea of spontaneity of the reaction, in which direction is favored or not, okay? So taking a look at the top there, right? Thermodynamically stable reaction, right? A delta G of plus 3.26, okay? So what does that mean, right? We're talking about it's not, right? It's not, it doesn't go in that direction. It's not spontaneous in that direction here. Okay. Thermodynamically unstable, right? Negative value for a delta G there. Okay. And then product favored but too slow to be important. Right? This is the kind of the quintessential example here, right? And then we make jokes about diamonds are forever, but they're not kinetically stable, ha ha ha, right? But what we mean is that it's practically speaking, right? The form of a diamond will slowly decay into graphite, but we're talking about millions of years, okay? And we could actually calculate the delta G value. You guys can do it, right, based off of the values for these in the back of the book, right? So it's kinetically stable, right? It's kinetically stable for graphite there, but the activation energy to do this is just not going to happen. Okay. So the point being this. Well, I guess the main point that I always think about when I'm thinking about this chapter is that we can use delta G to qualitatively predict, right, whether a reaction is product favored or not, okay? But still there's some other things we have to consider along the way too, all right? And that's why we don't end chemistry at the end of this chapter. Otherwise, all we'd have to do is calculate delta G for everything all the time, right? And you guys would know as soon as a reaction works or not. Okay? So the rest of the time that we spend in chemistry is kind of basically making a lot of arguments about whether things are kinetically or thermodynamically stable. Okay? So you'll definitely hear me talk about this stuff again when we go through organic chemistry with you guys. Which, by the way, it's getting to advising season, huh? We're towards the end of it. Right? So how many of you guys are coming to organic chemistry next fall? All right. It's not 8 a.m. though, right? What is it, 9 o'clock?
9:30.
Man, all right, you guys get the easy life now. But anyway, so keep this stuff in mind. And then I'll finally come through on my promises when I say that, hey, we'll see this again in organic chemistry. Okay? So cool. What we'll do, we'll talk about the exam on Friday there. And we will start going through some problems from this chapter and just kind of polishing a couple of the ideas that come out of it. Sound good?
Quiz will be on chapter 9.
Yeah, that sounds good.
Okay.
I have one more question.
Yeah.
When you say, we're talking about delta G for elements that are, elements that are,